Hello everybody, I hope you're doing well. Welcome back to another video in the Introductory Calculus playlist. So in the last video, we've talked about the idea of limits and how that can help us mathematically explain values that function are approaching, right? So if we had, an input approaching a certain value, what value does the output approach in a function? And we've also used limits to come up with a tool or a method to determine if a function is continuous at a given point. So while we're still going to continue talking about limits, I wanted to take a quick moment in this video to kind of reinforce some fundamentals of trigonometry that I think you should know. And the reason I wanted to reinforce these concepts is because later videos in the calc playlist will be using trigonometric functions, and I think it's good to make sure people get a quick refresher on trigonometry. So in this video, what is the objective? So we're going to be talking about the basics of trigonometry through the lens of the unit circle, right? So we're going to talk about basic trig functions. We're going to be talking about what's the intuition behind the unit circle and basically just go through with several examples to make sure we have a good refresher on this topic so that later videos in the calculus playlist will be much easier for you guys to digest. Okay, so let's get started. All right. Okay, so all right. So what do you need to really know about trig? So there's three fundamental trig functions. And you might have heard of them from, previous algebra classes. So we have the sine function, the cosine, and tangent. And the acronym I like to use, I'm going to write this in blue. Sorry about this, handwriting is legible. So the acronym you should be using is SOH-CAH-TOA. So what does this acronym mean? So this is simply a mnemonic that we use to remember how the sine, cosine, and tangent function are defined. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So let's draw a quick example. We use trig functions to describe right triangles, by the way. So here's a sample right triangle. And let's say it was 3, 4, and 5, right? You can confirm that this right triangle is completely valid by the Pythagorean theorem of 3 squared plus 4 squared equals 5 squared. So we know that this is valid. And let's say we have an angle right here and we call it theta. So sine of theta, right, is equal to opposite over hypotenuse, right? So the opposite side from this theta right here is this 4 and the hypotenuse is 5. So this is simply going to be 4 over 5. The cosine of theta is adjacent over hypotenuse, right? This is the CAH in the mnemonic. So this is simply going to be equal to 3 over 5 because this side is adjacent to theta. So this is the adjacent side and this is the hypotenuse. So this is going to be 3 over 5. And then we also have tangent of theta, which is equal to opposite over adjacent. So we see that from this theta here, the opposite side is the 4 and the adjacent side is 3. So this is going to be 4 over 3. So this is a quick refresher as to what sine, cosine, and tangent are with a simple example. And now that we understand those, I guess we can move on to the next topic of what a unit circle. So let's do that down here because I think we will need a pretty picture. Okay, so let's do the unit circle in let's do it in a different color. I think I will go with this bright medium orange right here. Okay, so we're going to be talking about the unit circle. And what is the unit circle? It's simply a circle with radius 1 centered at the origin. Okay, so let's let's move down a little bit on this whiteboard so that we have room to actually draw this unit circle. Okay, so we have this circle right here, right? We're gonna have a 1 here, a -1, +1 right here, and a -1. So we draw the circle right here, right? It's not a perfect circle, but I think we can make this work. And we have our center right here. So the way the unit circle works is through this trick, right? Sorry. Okay. So the way the unit circle works is through this trick, right? So this side here, the positive horizontal axis is kind of our reference, and we draw our radius accordingly. And where we draw the radius kind of affects the angle and affects what point on the circle we hit. Actually, I don't love this circle drawing though, so let's make it a little bit prettier. Okay, this should suffice. So we have this positive horizontal axis right here where my cursor is. This is our reference of the angle. And based on where we draw the radius, let's say we draw the radius right here, right? We'll be hitting a point right here. And let this point be x comma y. And we know that the circle has radius 1. So since the circle is centered at the origin, right? From the distance from any point on this unit circle, right, to the origin is just going to have a distance 1. So you know that like this radius is always going to have value 1 by definition, right? Now let's do something cool here, right? Let's use this color. Let's say we have this radius right here, right? And we're going to draw this vertical line right here, right? So this vertical line will be perpendicular, right, or form a right angle with this horizontal axis. So we actually indeed have a right angle right here. And based on where we draw the radius, there is a certain angle formed, right? I'm going to label that in yellow, right? So there's this angle formed right here. And remember that the positive horizontal axis right here is relative, right? So our point of reference is this horizontal axis, right? So here's our theta. Our theta is right here, right? And now what can we do here, right? We know that this point here is xy. So what does that tell us? Well, it tells us the following. We know that x is going to be simply this distance right here. We know that y is going to be simply this vertical distance. So what does this accomplish? Well, what this accomplishes is that we can quantify this point and translate it to sides of this right triangle. So if only we can find values of this right triangle, right, i.e. the legs, then we can identify what point this is, right? So how can we do that? Well, let's take advantage of what we've discussed earlier with sine, cosine, and tangent, right? We know that the hypotenuse is 1, and we know this angle is theta. So using our trig functions, we can identify the values of x and y. So what you see here is that, x, we know the following. Sorry about that. We know that x, yeah. So we know the following, right? So we see that to this theta right here, x is the adjacent side and y is the opposite side. So we know that cosine of theta, right, is equal to x over 1, which means x is cosine theta. And what do we know? We also know that y is the opposite side to this theta. So we can say that sine of theta is simply equal to y over 1, which means that y equals sine of theta. So in principle, this means that the point xy on the unit circle is really cosine theta comma sine theta. And what else can we conclude? Well, we know that y is the opposite side and x is the adjacent side. So we can conclude that tangent of theta equals y over x. And remembering that y is sine theta and x is cosine theta, this leads us to a fundamental fact about tangent. Tangent really can be expressed in terms of the sine and cosine functions as such. So we know right here that tangent of theta is just simply sine of theta over cosine of theta. And this can help us in a lot of ways. In that we really didn't need to know what tangent was, right? We just needed to know how we could find it, right? And the best part is we can find it in terms of sine and cosine. All right, let's make some room down here below so that we can actually do some fun examples of the unit circle. So in terms of this being a refresher video, um, one thing that's important to know about the unit circle is you want to really know your special angles because that will help us in the upcoming examples. So let me make some space down here. Okay, cool. So let's do some examples, right? So what we need to know here are the special angles, right? And all you need to know about the special angles really boils down to two types of triangles, the 45, 45, 90, and the 30, 60, 90. So these are the things you really should kind of commit to like making sure you understand. So this is the 45, 45, 90 triangle. So we have this right angle here, and we have 1, 1, root 2. And because the 1 and 1 are of same length, this is your 45-degree angle, and this is your 45-degree angle. So what does this tell us? Well, this tells us that the sine of 45 degrees, right? And you can pick which 45-degree angle you want, right? But the point still remains the same. Sine of 45 degrees is opposite side, which is 1, over the hypotenuse, which is root 2. So this is 1 over root 2. And rationalizing denominator, this is equivalent to root 2 over 2. And we also know that the cosine of 45 degrees is 1 over root 2 because adjacent side is 1 and the hypotenuse is root 2. And this is also going to be root 2 over 2. And we can find the tangent of 45 as opposite over adjacent, so that's going to be 1, right? So that should be pretty easy. I'm going to write the sine and cosine because you can kind of compute the tangent easily, right? As we've discussed earlier. Now here's the 30, 60, 90 triangle. So we have our theta here. This is our 30-degree angle, and this is our 60-degree angle. So this is going to be 1, root 3, and 2 by definition. So we know that the sine of 30 degrees is 1/2, right? Because opposite over adjacent, or opposite over hypotenuse, sorry. And the cosine of 30 degrees is root 3 over 2. And then we also know that the sine of 60 degrees is root 3 over 2. And the cosine of 60 degrees is 1/2. And you might be noticing a property here. You saw here that the cosine of 30 degrees is root 3 over 2, but the sine of 60 degrees is also root 3 over 2. So these numbers are the same. So maybe there might be a relationship between the sine of 60 degrees and the cosine of 30 degrees. And to that suspicion, you might actually be right. You will actually be right on that. We're going to like make that a little bit more formal later, but it's if you notice that, props to you. So we have this already established, right? Okay, cool. So we have special angles established. And now that you know the sine of 30 degrees, the cosine of 30 degrees, the sine of 60 degrees, the cosine of 60 degrees, and sine of 45 degrees, and the cosine of 45 degrees, you'll have all the information you need to kind of solve the basic unit circle problems that'll kind of make sure you're refreshed on the topic. So I guess we can go into examples, right? So let's make some room here, right? I'm going to change the color here to blue so that we can kind of get into examples, right? So this is going to be applying unit circle. So lots of examples is kind of the best way to learn. So we're going to go through a bunch of examples. So remember how I told you about the unit circle? We want to be able to use it to find sines and cosines of special angles. Well, we can do that given the information we have. So what do I mean by this? Let's say we wanted to find the sine of 120 degrees, right? Well, what am I going to do? Well, I'm not going to really punch this out into a calculator, right? One thing I will do is I will instead, right, draw a unit circle and see if I can identify something helpful. So we have this positive horizontal axis right here. We know that like maybe 30 degrees will be right here, 45 degrees will come here, 60 degrees will come here. So let's say 120 is an angle here. One thing to understand about the unit circle is when we're going in the positive direction, like if you're going 120 degrees, you're actually going 120 degrees in the counterclockwise direction, right? So this is the 0 degree mark. This is the 90-degree mark, 180 degrees, 270 degrees, and back here is 360, right? So if we're going 120 degrees, we're really going 120 degrees counterclockwise. So this is the 120-degree angle mark, right? Now what can we do here, right? Well, let's use a bit of geometry, right? We're going to do a trick that we did earlier, right? So if we draw this triangle right here, we have a right triangle here. But what do you notice about this angle, right? If this angle here is 120 degrees, then this remaining angle is 60 degrees, right? And because we know something about 60 degrees and we know that the radius here is 1, right? If we know that this angle is 60 degrees, this side must be 30 degrees, right? So you know that this is going to be negative 1/2 and root 3 over 2, right? By the definition of the 30, 60, 90 triangle. Why is this side negative 1/2? Because you're in the second quadrant, right? So x is negative here and y is positive. So what is the sine of 120 degrees? Well, all we have to do is just take the y coordinate, right, of this point. So the point here is negative 1/2 comma root 3 over 2, right? So because you know the x and y coordinates of this point on the unit circle, right? Sine of 120 degrees is simply equal to root 3 over 2. And because you know sine of 120 degrees, you're able to find the cosine of 120 degrees and tangent of 120 degrees and so on, right? Okay, let's do another example. Let's say we want to find the tangent of, let me think, let me pick a number. So let's say we wanted to find the tangent of 210 degrees, right? So what do we do here? We'll draw a unit circle, right? And we'll see 210 degrees. Well, it's in the counterclockwise direction, so I would probably put it, wait, hold on. Sorry about that. Yeah, so I would probably put that down here, right? So this angle here is 210 degrees. But what do you notice? Hold on. You notice that this part here, you went 180 degrees counterclockwise and then another 30 degrees over, right? So this angle here is just 30 degrees. So what is our triangle going to look like? Well, you have your point here, right? So we have our grid, and then this is 30 degrees, right? So, and you know the hypotenuse is 1, so this is going to be negative 1/2, negative root 3 over 2, by definition of 30, 60, 90. So what is tangent? This is just going to be sine over cosine, right? And we know sine is negative 1/2, right? And the cosine is this x coordinate, right? So this is negative root 3 over 2, right? So if you go through the math, right, this becomes 1 over root 3, which equals root 3 over 3. So you've been able to find the tangent of 210 degrees. Now let's make things a little bit more interesting. We have 3 new trig functions here we can introduce based on the sine, cosine, and tangent, right? So we have 3 new functions, right? Cotangent, cosecant, and secant, right? So cotangent is simply 1 over tangent of theta. The cosecant is 1 over sine of theta. And secant is 1 over cosine of theta. Okay, so these are some new trig functions, and we're just going to simply apply them like to examples, right? So let's make this a little more interesting. So for these examples that we've just done so far, we have gone in the counterclockwise direction. Let's say we wanted to find the secant of negative, let me think of a number. So let's say we want to find the secant of negative 300 degrees, right? And by the way, if you remember this from math, we don't have to express angles in just degrees. I'm just using degrees right now to make life easier, but we can even use radians, right? So we'll get into that a little later after this example. So let's say we want to find the secant of negative 300 degrees. Well, what am I going to do? I'm going to draw a unit circle and follow a similar approach. So let's see. So I go negative 90 degrees, negative 180 degrees, negative 270 degrees, right? Because remember counterclockwise is moving in the positive direction, clockwise is going in the negative direction. So because this angle here is negative, we're going to go in the clockwise direction, starting from the positive x-axis. So we go negative 90, negative 180, negative 270, and you need to go a little bit, you got to go negative 30 more, so you're right here, right? But what do you notice, right? You have gone negative 300 degrees like in the clockwise direction, right? But what do you have left? Well, I could have gone another 60 more degrees. So what can I do here? All you have to do is you realize that the triangle is simply going to be this, right? The key to these unit circle problems is kind of drawing this unit circle out and figuring out where you land up when you spin like in the clockwise or counterclockwise direction. So you have this triangle that's 60 degrees here, right? And you have a 30, 60, 90, right? Hypotenuse is 1. So you know this is 1/2. This is root 3 over 2. So what is secant, right? Secant is 1 over cosine, right? But what is cosine? It's just simply this x coordinate right here, right? So we know that cosine of 60 is 1/2. So secant of 60 degrees is 1 over 1/2. And that's going to be 2. So you've solved secant of negative 300 degrees. Now, I was mentioning earlier about the idea of degrees to radians. Let me make that into a separate section, right? So this is going to be the degrees to radians section. Okay, so degrees, radians. So you can convert between degrees and radians. One difference between degrees and radians is that radians tend to be unitless, and you'll see radians a lot more in the calculus playlist, so it's good to get familiar with them. So when you want to go from degree to radian, multiply by pi over 180. If you want to go radians to degree, multiply by 180 over pi. So here's an example, right? Convert 540 degrees to radians. So this will be 540 degrees over 1 times pi radians. You can omit the units, but I'm writing the units here to make it, memorable for you guys so you can see what I'm doing. So you just simply multiply by pi over 180, and this is 3 pi radians, right? Let's say we wanted to convert pi over 6 radians to degrees. So this will be pi over 6 multiplied by 180 degrees over pi, right? Remember the conversion factor right here. Pi radians is 180 degrees. So this is going to be 30 degrees. So now that we have this established, we can kind of continue with our examples. I just wanted to make sure you guys remember that conversion because I might be doing examples that use radians. So let's do that. Okay, so now we've gotten a hang about converting, when when you have the degrees, right? Finding sines, cosines, tangents, cotangents, etc., right? And it's all a matter of drawing the unit circle and kind of applying the formula, right? But let's do some examples, but with radians. So let's say we wanted to find the cotangent of, let me think of a good example. Let's say we wanted to do it for 16 pi over 6. So let's say we want to find the cotangent of 16 pi over 6. So you know that this angle is going to be in radians, right? Now what do? We're going to draw a unit circle, right? So remember the positive horizontal axis is the 0 like radians mark, right? Like it's 0 degrees, so it's 0 radians, right? When we went 90 degrees in the counterclockwise direction, 90 degrees is equivalent to pi over 2 radians. So this is going to be 3 pi over 6 radians. And then here, this is 180 degrees, so pi radians is equal to 180 degrees. So this guy is going to be pi radians, so this is going to be 6 pi over 6. And then down here, this is 270 degrees, so this is going to be 3 pi over 2 radians. So this is going to be 9 pi over 6. And then this is 12 pi over 6. So what we realize is we go around in a full counterclockwise direction, you're at 12 pi over 6. Then you go back to this 3 pi over 6 mark, so it's 15 pi over 6. And then you go one more pi over 6 across, and now you're at 16 pi over 6. So what happens? This is where you end up at, right? And if you look at the triangle, right, you went an extra pi over 6 from this 3 pi over 6 to this 4 pi over 6 mark, right? And then if you want to come back to this horizontal line, you had to go 2 pi over 6 units more, right? But what is 2 pi over 6? Well, that's simply pi over 3. So this angle here is just pi over 3. But what is pi over 3? Well, pi over 3 in degrees is 60 degrees, right? So we can draw our triangle, right? So this is going to be negative 1/2 root 3 over 2. And this is going to be hypotenuse 1, right? And now the cotangent is simply going to be 1 over the tangent. And remember how tangent was sine over cosine? This is just going to be cosine over sine. But what is the cosine? We know it's negative 1/2, right? And we know the sine is root 3 over 2. So this cotangent is going to be negative 1 over root 3. And if you simplify this, this is going to be equal to negative root 3 over 3. But this is how you find the cotangent, right? And the angles and radians. So the trick for these is just kind of like drawing the picture out, right? And labeling these marks. And then you just kind of, circle around until you reach where you want to. Let's do one more example so that you guys are getting the picture, right? Think one more example help on this. Okay, let's suppose we wanted to find the cosecant, right? Let me change this color to blue. So we wanted to find the cosecant of, let me think of a number though. Let's try the cosecant of negative 13 pi over 4, right? So how are we going to do this? Well, we draw the unit circle again, right? And remember that because this angle is negative, we're going in the clockwise direction, right? So you're at 0 right here. This is negative pi over 2, right? So this will be negative 2 pi over 4. This is going to be negative pi, so this is negative 4 pi over 4. This is negative 3 pi over 2, right? So this is negative 6 pi over 4. And this is going to be negative 8 pi over 4. So now we go. Negative 2 pi over 4, negative 4 pi over 4, negative 6 pi over 4, negative 8 pi over 4. Okay, we're not yet at negative 13 pi over 4. So then if we're at negative 8 pi over 4, then we're going to go negative 10 pi over 4. And then we're going to go negative 12 pi over 4. Right? So you're back here. And now you go negative 13 pi over 4. Here, this is negative 12 pi over 4, right? Then we go another negative pi over 4, and we're right here. So what does this triangle become? Well, this triangle is simply this, right? So this is going to be the pi over 4 angle, right? And you remember that pi over 4, if you convert this to degrees, this is 45 degrees, right? So this is going to be negative 1 over root 2, 1 over root 2, 1. Remember the 45, 45 triangle. If you wanted to make this simpler, this could be negative 1, 1, and root 2. But the idea holds the same, right? Whatever way floats your boat here. So we have this pi over 4 reference angle, as we call it, right? So the special angle we draw right here after we kind of figure out where you're ending up at from spinning in the clockwise or counterclockwise direction. This angle here in green is what we call a reference angle. But now that we have this reference angle, we can find the cosecant easily. So you remember that the cosecant is 1 over sine, right? But what is sine? It's just simply 1 over root 2, right? So this is just going to be 1 over root 2, right? And this is going to be root 2. And that's all there is to it with these examples. So I can imagine, like, if I give you an angle like this, right, in radians or degrees, you should be able to easily draw a diagram like this and kind of figure out the values of the trig functions. Okay, so now that we have this, right, let's move on to a more interesting case, right? So let's move down here. There's one more cool thing I want to highlight about the unit circle. And this is what we call coterminal angles. And you might have actually seen it before, but it's good to remember how it works. So let's move this in red. So we have another term called coterminal angles. So what is a coterminal angle? So let's say on the unit circle, we were drawing pi over 6, right? So one way of doing that, so pi over 6 would be right here, and here's pi over 6, right? But one thing you might realize is, wait, when I draw pi over 6, I'm going in the counterclockwise direction positively, but couldn't I draw the same angle by simply going enough degrees in the clockwise direction? And you are 100% right. So if you're at this pi over 6 mark here, you'll realize that, wait, I can go negative pi over 2 degrees right here, negative pi degrees, negative 3 pi over 2 degrees, and then I go negative 2 pi over 6 degrees more, or radians more. Sorry about that. So this is going to be negative pi over 2, negative pi. This is going to be negative 3 pi over 2. And then this angle here is going to be negative 2 pi over 6. So this angle shown in green is simply negative 3 pi over 2 plus negative pi over 3. And that's simply going to be equal to negative 9 pi over 6 plus negative 2 pi over 6. So this is going to be equal to negative 11 pi over 6. So this angle in green of negative 11 pi over 6 reaches the same point that you would have gone if you had gone pi over 6 in the counterclockwise direction, right? So negative 11 pi over 6 is what we call coterminal to pi over 6. Now, through this observation, can we come up with an easy algorithm to figure out, like, if I am given an angle, find all the coterminal angles, right? Or all the angles coterminal to it. In fact, if you wanted to be creative, right, negative 11 pi over 6 isn't the only equivalent angle to pi over 6, right, that reaches the same point. What if I had gone, in one 360-degree clockwise spin and then went negative 11 pi over 6, counterclockwise? Wouldn't that be still an equivalent angle? And yes, it would, right? Because you spin a full 360 counterclockwise, right? And then you go negative 11 pi over 6, again clockwise, and you reach the same point. So this brings us an algorithm to find coterminal angles. So angles coterminal to pi over 6 is pi over 6 plus 2 pi n. Remember that 360 degrees is simply 2 pi radians. So all the angles that are coterminal to pi over 6 is simply pi over 6 plus 2 pi n. And n is any integer, right? Positive or negative, right? So this expression here will get you all equivalent angles to pi over 6 in the unit circle. And you can come up with another angle. Let's say we looked at the angle of 5 pi over 4, right? If you wanted to get all the angles coterminal to 5 pi over 4, it would be 5 pi over 4 plus 2 pi n, where n is an integer. So hopefully that gives you a refresher on coterminal angles. The last thing I wanted to kind of touch upon is a couple properties of trig that we can kind of discover using the unit circle. So here's a couple properties of trig you might remember, but I think it's worth describing with the unit circle. So what else can we discover with the unit circle? And here's another cool property. Let me make this discover with the unit circle. Here's a property we can discover. So remember we have this unit circle, right? It's a circle with radius 1. And every point xy is defined a special way, right? So we have this radius of 1 right here. And then, and then we have this special point right here. This is going to be x comma y. And we have this theta right here. And what we can do with this is we can kind of use a trick we discovered by drawing this right triangle right here. So what do we know, right? Well, we found out, right, that x maps to cosine of theta and y maps to sine of theta. But what happens though? We have a right triangle here, right? With a hypotenuse 1. This side here is essentially cosine of theta, and this vertical side here is essentially sine of theta, right? And we have our theta right here. So what happens? Well, if this is a right triangle, the Pythagorean theorem must satisfy, right? So we know that sine of theta squared plus cosine of theta squared equals 1. So this is what we call a Pythagorean identity. So sine squared theta plus cosine squared theta equals 1. So this is a very important identity, and it will definitely come in handy. Now, what else can we do here? We can express equivalent formulations, right? Let's say we divide this expression like on both sides by sine squared of theta. So we have sine squared of theta plus cosine squared theta equals 1. And then we divide both sides by sine squared theta. So this formulation brings us to the following, right? Doing this operation, it brings us to another helpful identity. And it's actually equivalent to the original identity because we're dividing both sides by sine squared of theta. So we're not really changing the value. So this is going to be 1 plus, what is cosine over sine? That's cotangent. And because we're doing cosine squared over sine squared theta, this is going to be cotangent squared theta. And what is 1 over sine squared theta? Well, remember that 1 over sine is cosecant, right? And thus 1 over sine squared theta is going to be cosecant squared theta. And likewise, if you divide both sides, right, of the sine squared theta plus cosine squared theta equals 1 by cosine squared theta, we get that tan squared theta plus 1 equals secant squared theta. So now that you have these three equivalent identities, if I was doing a unit circle problem and somehow I knew that cotangent theta is some value, right? Could I find the value of cosecant squared theta? And we'll actually do an example of that real quick because I think it's a valuable example to make sure you guys really kind of understand the power of these identities. Now, you don't have to use these identities necessarily. There's other ways of doing it, like a visual way, and I'm going to go with the visual way, but you can use these identities to kind of verify the answers, right? So let's suppose we know the following, right? Let's say we know that cosecant of theta is 3/5. Find cotangent of theta. Okay, so how are we going to do this? Well, we're only given that cosecant theta equals 3/5. So that's the best information we have, and we have to work with that. But luckily, we can draw a right triangle to solve this problem. So we have our right triangle right here, and we have our theta. So if cosecant of theta equals 3/5, cosecant of theta is 1 over sine theta, right? So you know here that sine of theta is 5/3. So this is going to be 5 over 3. Well, this is actually kind of a bad example because we get an invalid right triangle here. So let me change the number a little bit to make it so that it's a little bit more reasonable. Well, actually, let's make cosecant theta 9/5. Okay, so now we know here that sine of theta equals 5/9. So you have a 5 here and a 9 here. Now, because you have these two sides, we can figure out the third side. This is going to be the square root of 9 squared minus 5 squared, right? By the Pythagorean theorem. So this is just going to be the square root of 81 minus 25, which is 56. And that's going to be 2 root 14. Okay, cool. Now we can find cotangent of theta, right? Cotangent of theta is going to be 1 over tan theta, or cosine of theta over sine of theta. So we know that tangent of theta, right, from the looks of this is 5 over 2 root 14. So that implies that cotangent of theta is 2 root 14 over 5. And bam, just by knowing the value of one trig function, we can figure out the value of all the other trig functions. Imagine if I change this question to finding the value of cosine of theta. Well, we would proceed exactly the same way, because once we get like what the value of one trigonometric function, we know the value of a hypotenuse or a leg, or the value of two of the legs, and then we can find the value of the third side. And then now that you have the theta established and the values of the legs and the hypotenuse, we can find the values of all the other trig functions easily just from straightforward definitions. So this is a quick example I want to illuminate to understand the beauty of some of these trig functions and what this can help us find, right? And the last identity, or the last trick I wanted to go over, is something you have noticed in some of the past examples. So you have noticed, if we go back up to our whiteboard right here, let's scroll up. So when we scroll up here, right, you've noticed here that the sine of 60 degrees is root 3 over 2. And the cosine of 30 degrees is also root 3 over 2. And how could this equivalence be, right? Is there some sort of equivalence here that, generalizes to all angles? And the answer is yes. So let's show that more formally, right? So what do we want to do here, right? We have this right triangle here, right? And the values are A, B, C, right? So we have theta right here as a value, right? So if this angle is 90 degrees and this value here is theta, right? Then the other angle is going to be 90 minus theta. And already you see the following, right? Just from first glance, sine of theta is A over C, but that's also equivalent to the cosine of 90 minus theta. And likewise, the cosine of theta is B over C, right? But if you look at the picture, that's the same thing as sine of 90 minus theta. So what you've done here, right, is you've established a way to relate both the angles, right, other than the right angle, obviously, right, to trig functions, right? You've related the value of the trig functions from, this data here to the values of the same trig functions by using this angle. So this is kind of a cool property to kind of discover, and hopefully these examples kind of help you to give a good refresher on the value of the unit circle and the tremendous power you get and what you can find and do with it. So hopefully this video gives you a good refresher, and please like and subscribe because I spend a lot of time, making sure the explanations are very intuitive and accessible to people who are currently studying calculus or want to refresh calculus, but it's been a long time since they've taken a calculus course. So yeah, hope to see you in the next video where we will cover examples of solving problems with limits, and hopefully the stuff from this unit circle will carry forward into the future videos in this playlist. So thank you very much for watching and have a good rest of your night.